Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to learn how to name organic compounds that contain the amide functional group. And so before we get into the details of naming organic compounds that contains an amide, we need to first learn the structure of an amide and how to classify it. And so it turns out that amides belong under the carbonyl family, meaning that this functional group has this very distinctive carbonyl group. And what makes this carbonyl group an amide is that its carbonyl carbon is covalently bonded to this nitrogen. And in turn, this nitrogen is going to be covalently bonded to two of these R groups. And so the identity of these R groups can either be a hydrogen or an alkyl group or an alkyl chain. And so depending on the identity, depending on whether or not the R group is a hydrogen or an alkyl chain, it will dictate whether or not this amide is considered a primary amide, a secondary amide, or a tertiary amide. And so it also turns out that amides are simply derivatives of carboxylic acids. So looking at this structure down at the bottom, here we see this hydroxyl group that's covalently bonded to carbon of the carbonyl group. And so instead of a hydroxyl group, it's going to be an amine. And so if an amine is covalently bonded to this carbonyl carbon that belongs to the carbonyl group, then this whole structure is going to be referred to as an amide. And so if you guys recall from the previous lecture video, amines are classified as primary, secondary, and tertiary. And so that classification carries on to amides as well. And so if the nitrogen of the amide is covalently bonded to one carbon, and it doesn't matter if that carbon is part of the carbonyl group, it's a carbon, then this is known as a primary amide. And so if you guys notice, this primary amide contains two hydrogens, very similar to a primary amine. A primary amine has a nitrogen bonded to two hydrogens, bonded to one R group. And so just as long as there is one carbon that's covalently bonded to one nitrogen, you have a primary amide. So a secondary amide means that this nitrogen is covalently bonded to one carbon, two carbons. And so if you look at the number of hydrogens that this secondary amide has, it only has one hydrogen. For tertiary amides, there are no hydrogens on the central nitrogen. Rather, this central nitrogen is covalently bonded to 1, 2, 3 carbons, where the R group is going to represent an alkyl group. And so these two R groups can be the same or they can be different. It doesn't really matter its identity, just as long as this is carbon-based and this is carbon-based. And so if this R group is a hydrogen, then we don't have a tertiary amide, we have a secondary amide. Okay, so amides can also be found in a ring. And so the most common amide is this 4-carbon or 4 vertice ring, if you will. And so this is known as a cyclic amide. And cyclic amides are called lactams. And so these lactams are, you know, prevalent in the penicillin family. So the penicillin family is an antibacterial. It's a bactericide. And so what that means is that this drug has the ability to kill the bacteria. And the mechanism of that action, it's pretty interesting. It's pretty specific. So penicillin kills the bacteria through binding of the beta-lactam ring, which is this, to an enzyme called transpeptidase. And so transpeptidase, its main function is to cross-link the cell wall, making the cell walls sturdy, if you will. And so what penicillin does is that it binds into the active site of transpeptidase, and this beta-lactam ring undergoes a specific reaction so that it opens up, this ring will open up, and a covalent bond will be formed with a carbonyl carbon of the penicillin or penicillin derivative to one of the amino acids that's found inside transpeptidase. And that covalent bond kind of keeps this penicillin inside the active site of the transpeptidase. And so if you guys can imagine that you have this enzyme here in which the penicillin is permanently stuck in the active site, nothing else can come in. And so if it does try to come in, for so to speak, it'll just like bounce right off because that space has been taken up by penicillin. And so since transpeptidase has lost its function, its ability to cross-link the cell wall will no longer be possible. And so without a formidable cell wall, a bacterial cell will be vulnerable to fluctuations in osmotic pressure between the inside and outside of its cell membrane. And so in a hypotonic solution, we have all of this water that's going to rush inside the it's going to rush inside the bacterial cell. And since there's no cell wall to kind of keep to resist the osmotic pressure, what's going to happen is that the bacterial cell will explode. And if you explode the bacteria cell, then it's dead. Oh, my screen froze. Okay. And so looking at the biochemistry of this penicillin and its action inside the target enzyme, it's pretty cool to kind of study because it has all of these domino effect that essentially leads into bacterial death. And so penicillin doesn't directly kill the bacteria. I just want you guys to be clear on that. It is the osmotic pressure that does the physical killing of the bacteria. But penicillin plays a strong role because it makes the cell wall, the bacterial cell wall, vulnerable when these bacterial cells replicate. And so when the bacterial cells replicate, that's when the bacteria really needs the transpeptidase so that it can recreate the cell wall. Okay. And so if your bacterial cell does not replicate, then technically speaking, your penicillin won't have any action on it because the transpeptidase is not as active as it is when those bacterial cells are undergoing replication. All right, so we're going to skip polarity of amides, IMF. We're going to skip all of this stuff. And so I want to focus on this slide here just to kind of demonstrate where amides can be found. And so Amides can be found in a lot of organic compounds, biomolecules, proteins, for example, silk, nylon, the list continues. And so looking at this organic compound, which is melatonin, and melatonin has been, so melatonin has gained a lot of popularity as a supplement to help individuals who have trouble sleeping sleep. And so melatonin has an amide, and the amide is right here. So notice that this nitrogen is covalently bonded to 2 carbons. So this amide is a secondary amide. And it's pretty common for a lot of these bioorganic molecules to have more than one type of functional group. And so here we see an amine in a heterocyclic form. And we also see an ether. So ether is a carbon, oxygen, carbon. So looking at acetaminophen, which is the active ingredient in Tylenol, we see an amide. And so this nitrogen is covalently bonded to 2 carbons, so making this a secondary amide. We also see the presence of an alcohol or a hydroxyl group in acetaminophen. So looking at these two structures, we have penicillin G once again and amoxicillin. And so amoxicillin is a derivative of penicillin. So notice that they have the same type of structure. We have a carboxylic acid, COH. We have an amide, or specifically a lactam, since it's in a ring. We have a lactam again. So here we have an amide. And what makes amoxicillin different than penicillin is 2 functional groups. So here we have a primary amine, and we have an alcohol or hydroxyl group. So notice that there is no primary amine found in penicillin, and there's no hydroxyl groups. And so by adding these extra functional groups, decorating this compound with new functional groups, it'll make this drug less susceptible to bacterial cells that have resistance to, for example, penicillin. And so it's cheaper to repurpose a drug that works by decorating it with functional groups. And then, after you've decorated it with a functional group, you can perform, enzyme assays or kinetics or whatever enzyme experiment you want to perform to assess its effectivity for that specific enzyme drug target. And so this is not a this is not a drug design class, so let's not get into the details. All right, so amides are also found in macromolecules such as proteins. And so when you guys study proteins in your biology class, you guys have these different levels of protein structure. So primary structure, secondary structure, tertiary structure, quaternary structure. And so for proteins in the primary structure, when the carboxylic acid of the backbone of the amino acid undergoes a dehydration with the amine of the amino acid, it's going to form this peptide bond. And this peptide bond is just a fancy name for an amide. And so fibers in wool, they also have many amide linkages that gives it its distinctive strength and flexibility. My screen is frozen again. And so amides are also found in industry. So for example, nylon, it's a polymer. And these amides are formed through a dehydration reaction. So in other words, it's releasing water. And so if I zoom in, we have this, this diamine substance, and we have this dicarboxylic acid substance. And when the carboxylic acid reacts with the amine, the hydroxyl group and one of those hydrogens from the amine is going to combine to form water. So we have a dehydration reaction. And that dehydration reaction will form these amide bonds. And depending on the structure of this repeating unit, you can get, for example, nylon or a different type of polymer that has different physical and chemical characteristics. And so in terms of preparing amides, we kind of saw it in the previous slide over here. In terms of synthesizing amides, this process is known as amidation. And so amidation is nothing more than reacting a carboxylic acid with an ammonia, a primary or secondary amine, and in the presence of heat. And so if you guys have a carboxylic acid and it's reacted with, for example, ammonia or a primary amine, the hydrogen, one of the hydrogens from the nitrogen, from the amine or the ammonia, is going to react with a hydroxyl group that's in that carboxylic acid. And so this is going to form H2O, so a dehydration reaction will occur. And when this water molecule leaves, that'll create a covalent bond between the carbon and the nitrogen, forming an amide bond. And so there's some trends here. If you guys have ammonia, and if you react it with a carboxylic acid, what you get, my screen is frozen again. What you get is a primary amine, or I'm sorry, primary amide. Okay, so that's our recipe. If you guys have a carboxylic acid and ammonia, you treat it with heat, you guys will get a primary amide. Now, if you guys react a primary amine, such as methylamine or methylamine, with a carboxylic acid, what you get is a secondary amide. Okay. And so if you guys, my screen is frozen again. And so here if we have, for example, another carboxylic acid and a secondary amine, so we'll just go ahead and keep it as methyls. So this is a secondary amine. When a dehydration reaction occurs, that's going to remove the water molecule, allowing the nitrogen to be covalently bonded to this carbonyl carbon. My screen is frozen. And so what you guys get is an amide with two methyl groups. And if you guys count the number of carbons, then there is 1, 2, 3 carbons on this nitrogen. And so therefore, you get a tertiary amide. Okay. So just keep that in mind. If you guys have ammonia with a carboxylic acid, you get a primary amide. If you have a primary amine and a carboxylic acid, you guys will get a secondary amide. When you have a secondary amine and you react it with a carboxylic acid, you get a tertiary amide. And so tertiary amines cannot undergo amidation because tertiary amines do not have the hydrogen that's on a nitrogen. Okay. And so just to demonstrate this, let's just say that we have this 3-carbon carboxylic acid. Remember that amidation requires a dehydration reaction to occur. So if you have a tertiary amine, this tertiary amine has no hydrogens on the nitrogen. And so therefore, it cannot undergo a dehydration reaction in the presence of heat. It'll stay as is. Okay. And so let's go ahead and quickly draw the product here. So we have heptanoic acid and diethylamine. So if we have heptanoic acid, we have a 7-carbon carboxylic acid. So that's 1, 2, 3, 4, 5, 6, 7. And so on the 7th carbon, we have our carboxylic acid. And so it's being reacted with diethylamine. And so for diethylamine, we have nitrogen with 2 ethyls. And so if we have 2 ethyls, and if we want to make sure that the nitrogen has the full octet, then that means that there's a lone pair present and there's at least 1 hydrogen. And so overall, this is going to be a secondary amine. Now when you guys react both of these together, this is going to go away. It's a dehydration reaction. And what you guys will get is a covalent bond between the carbonyl carbon and the nitrogen itself. And so this is the product of heptanoic acid and diethylamine. So let's go ahead and look at this reaction. We have 3-ethyl-4-methyl hexanoic acid. And so since I have hexanoic acid, I have a 6-carbon compound. So 1, 2, 3, 4, 5, 6. And then on the 6th carbon, remember that carboxylic acids are always terminal. I'm just going to go ahead and draw my carboxylic acid. And so this carbonyl carbon becomes carbon number 1. So here I have an ethyl on carbon number 3. So 1, 2, 1, 2, 3. So I have an ethyl here. And on carbon 4, I have a methyl. So this is my this is the structure of my carboxylic acid. Looking at the amine, I have a trimethylamine. So trimethyl means I have 3 methyl groups, and that would be it. So remember that there's a lone pair on that nitrogen. So if you guys count the number of electrons surrounding nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. And so it has the full octet. In other words, there's no extra hydrogens on the nitrogen. And so this is a tertiary amine, meaning that no reaction will occur. It needs to have that hydrogen so it can undergo a dehydration reaction. So looking at this next example, we have but-2-enoic acid. And so this just means that on carbon 2 there's going to be a double bond. Another way to name this is 2-but-tenoic acid. All right, so since we have a butene, it is a butene, we have a 4-carbon compound, 1, 2, 3, 4. We know that carboxylic acids are always terminal. And so on carbon 2, we have a double bond. So this is carbon 1, this is carbon 2. So we have a double bond. And we're going to react this with ammonia. And ammonia is NH3. And so since there is at least one hydrogen on this nitrogen, this can undergo amidation such that this OH and H is going to form water. When that forms water, so I'm going to go ahead and erase those because that becomes a water molecule. That forces the carbon and the nitrogen to create a covalent bond between each other. And so this is going to be, well, actually, let me just draw this a little bit better. We want to maintain that trigonal planar geometry as best as possible. And so this is going to be the product of 2-butanoic acid reacting with ammonia. So notice we get a primary amide. All right, so just to list it out, if you have COOH reacting with with NH3, you get a primary amide. If you have a carboxylic acid reacting with RNH2, so this is a primary amine. Let's see here. What you get is a secondary amide. If you have a COOH reacting with a secondary amine, you get a tertiary amide. All right. And so hopefully going through those 3 examples, you guys will, hopefully you guys understand how to predict the products. And so let's just say that this, before I move on, let's just say that this amine was not tertiary. Let's say that we have a secondary amine. So what that means is that we have a hydrogen. And so if we have a secondary amine, then that means that the OH and the H is going to come together to form water. So it's a dehydration reaction in the presence of heat. And so I'm just going to go ahead and erase these components because we know that they are going to form water. So I'm going to go ahead and bring this nitrogen closer to the carbonyl carbon. I'm going to go ahead and erase this covalent bond where that hydrogen used to be. and I'm going to put a covalent bond between the carbonyl carbon and that nitrogen. So notice I get a amide, right? So this is my amide, and this amide is 1, 2, 3 carbons. So this amide, the nitrogen in this amide is covalently bonded to 1, 2, 3 carbons, thus producing a tertiary amide. Okay, much like what I mentioned here. All right, so you guys have an example of each and every single one of these reactions. I know I didn't write it in full, but hopefully, and in the very end, I just drew the final product, but hopefully you guys understand how the reactants was transformed into the product that you guys see. All right, so now that we have a stronger understanding of amides, we know what they look like, where they're found, how it's formed, how it's created. Let's go ahead and talk about naming these amides. And so since these amides have 3 different classifications, primary, secondary, and tertiary, we're going to go through and look at the rules on how to name, for example, primary amides versus secondary amides versus tertiary amides. So let's go ahead and start. And so to name a primary amide, the first thing that you need to do is find the longest consecutive carbon chain, and that has to be derived from the carboxylic acid. Another way to see this is find the longest consecutive carbon chain that connects to the carbonyl group. And so I'll probably use that instead of this rule that I typed out. And so here I've identified my carbonyl group. I'm going to find the longest carbon chain, which is essentially this. And so this is going to be my parent chain. And so I'm going to replace the oic acid ending, or you can even do it with the E, like what we've done in the past, where we drop the E and then add the suffix. In this case, the suffix is amide instead of amine. And so here in this case, it's not necessary to indicate the position of the amide in the compound unless you actually have to, and there might be some cases in which you do. The carbonyl carbon is given the lowest possible carbon number. And so for primary amides, the primary amides are terminal. In other words, there is no carbon chain that's bonded onto the nitrogen. And so since amides are terminal, we don't need to communicate to the reader the carbon number of where this amide is. We always know that this is always going to be carbon number 1. So the carbonyl carbon is going to be carbon number 1. And we'll go through some examples to highlight this. Actually, we'll name this one. Okay. All right. And so my first step is to identify my carbonyl group, because that originally belonged to the carboxylic acid. If you guys don't want to use that perspective, that's fine. Just identify your carbonyl group. Find the longest chain here and here. So name that. So that is 3 carbon. So I can just say propane. If you want to say propanoic acid to follow the rules, you can. You'll still get the same answer if you were to stick with this ane ending or ene ending or whatever. And so you're going to go ahead and drop the E, and you're going to add amide. And so instead of propane, it's going to be propanamide. And so since there are no other substituents that's found on this carbon chain, that's pretty much it. I mean, the moment you say amide, you've already described this. And we know that amides, primary amides specifically, are terminal. And so therefore, where there used to be a 1' propanamide to describe that, hey, you know, this amide is on carbon number 1, excuse me, not 1 prime, this carbon is carbon number 1, it's not necessary for you to indicate the position of the amide since primary amides are terminal. Hopefully that made sense. Okay, so let's go ahead and look at a few more examples. And after going through these examples, hopefully you guys get the pattern on how to name these amides, primary amides specifically. So looking at this carbon, this organic compound, automatically I recognize that this is a primary amide. There is my carbonyl carbon, and so anything that's attached, any carbons that's attached to the carbonyl carbon is probably going to be my consecutive carbon chain. So I have 1, 2, 3, 4, 5, 6. And so since I have 6 carbons, I have hex. I have to use hex. Since they're all single bonds, it's going to be hexane. Drop the E, add in the amide. So this is going to be hexanamide. Since there are no substituents on this carbon chain, it would simply be hexanamide. And so let's go ahead and use this same organic compound, and I'm just going to add, for example, these 2 substituents. So let's just say that there are substituents on this carbon chain. How would you name that? Well, since now I have substituents, I have to figure out my numbering system. Remember, my functional group is amide, and we want our main functional group to have the lowest carbon number possible. So therefore, this carbon is carbon number 1. This is 2, 3, 4, 5, and 6. And so what that means is that I'm going to build upon this parent name to include my substituents. So it looks like I have, oops, oh, okay. So it looks like I have a 3-methyl, and here I have a 4-chloro. So since I have 2 different substituents, I have to organize them. I have to list them alphabetically. So the C comes before M. And so here in this case, I have to describe my chloro first. So this is 4-chloro. And then I'll have my 3-methyl. And so I don't need to indicate that this is going to be carbon 1, right? That's not necessary because I have a primary amide. And primary amides are always terminal. And so this is going to be the name of this organic compound. Okay, so I just added my substituent in front of my parent name, which is hexanamide. Okay, so let's go ahead and focus on the next compound. Here I have my carbonyl, so this is carbon 1. I have my primary amine. And so I have my second carbon. And so since I have a 2-carbon compound with my amide, this is going to be ethane. Drop the E, put in amide. So this is going to be ethanamide. And that's pretty much it. So let's go ahead and look at this next organic compound. Here I have my primary amine, or sorry, primary amide. And so I know that this is carbon number 1. I have 1, 2, 3, 4 carbons. And so if I have 4 carbons, then this is going to give me bute or butane, since I have single bonds. Erase the E, put in the amide. This is butanamide. And it looks like I have a bromine on carbon number 2. So I'm going to put 2-bromo. And then since I don't need a number to describe where the amide is located, since it's always terminal, in other words, it's carbon number 1, I'm just going to go ahead and put those two pieces together and say 2-bromo butanamide. And that is the name of my structure. Now, what if I were to put a double bond here? Okay. Well, that would change the name of my parent name. And so instead of it being butan or butane, this would now be butene. And so I need to erase the E, add the amide. And once again, I don't need to, since this is a primary amide, I don't need to put in the carbon number. But I do need to indicate to my reader where this double bond is going to be located. And it turns out that in this structure, it starts on carbon number 3. So I'm going to put 3-butanamide, meaning that the double bond is on carbon number 3. And so if I were to include the 2-bromo, I would just simply put 2-bromo in front of the 3. And then put a dash to separate the 2. And so the name of this structure that you guys currently see with a double bond is going to be 2-bromo-3-butanamide. And that would be the name of that compound. Okay. All right. So looking at our last, let's call this our last example. Once again, here we have this primary amide. This is carbon number 1, carbon 2, 3, 4. Looks like we have a 4-carbon compound. And once again, I don't see any double bonds, so this is butane. I'm going to drop the E, add the amide. So this is butanamide. Since I have a primary amide, I don't need to put in carbon number 1 in front of butanamide, so I don't need to put this guy. But I do have a methyl on carbon number 2, and so I'm going to finish this off by writing 2-methyl and then butanamide. Okay. So hopefully by going through those examples, you guys have an idea of how to name primary amides. And hopefully you guys, you feel comfortable naming these primary amides. So I'm going to go ahead and skip the cyclic rings. I believe the answer is in your PowerPoint if you guys want to challenge yourself. And so I'm going to go ahead and move on to secondary amides. And so for secondary amides, once again, we're going to find the longest carbon chain that's derived from the carboxylic acid. And we're going to use a suffix amide to represent that we have our functional group amide. And so here for secondary amides, we actually might have to indicate the position of the amide. I think, I can't remember. And so if the secondary amide is on like carbon number 2, then go ahead and include that position, include that number in your naming. But if all of the amides are terminal, I think they are, I'm trying to think. Yeah, I think they're all terminal. I could be wrong. Anyways, we'll look at some examples. And so if basically we get something that looks like this with an R group. Yeah, for secondary amides, you guys do not need to put the name, or you guys don't need to put the number. Just because if you have CON and then another carbon, this is going to be the longest. This is going to describe the carbon chain. And so with the amide, it's always terminal. So in this case, you guys do not need to indicate the position of the amide in the compound. So that holds true. And so once again, the carbonyl carbon is given the lowest carbon number. For secondary amides, very similar to secondary amines, you're going to be using the capital N to designate the smallest alkyl group that's attached to the nitrogen atom of the amide. And this is going to be described first before any substituents, much like you guys saw for secondary amines and tertiary amines. So let's go ahead and look at some examples. And so I recognize that this is my carboxylic acid, so any carbons that's attached to the carbonyl carbon is probably going to be my parent chain. So that means that this carbon that's attached to the nitrogen is going to act as my N substituent. So this is going to be N-methyl, very similar to what you guys did for amines, secondary amines and tertiary amines. And so this, since this is carbon number 1, this is going to be carbon 2, 3, 4. And so to name my parent chain, I have a 4-carbon compound, so that's probably going to be butan. Since they're all single bonds, this is butane. Erase the E, add the amide. So this is butanamide. And so since this is carbon number 1, there's no point for me to put the 1 in the very front. And so since I don't have any other substituent on my chain, my final answer is going to be N-methyl butanamide. And so what if we added, for example, we erased this 2 and we added, for instance, I don't know, this iodine. And so we would have to describe this iodide that's on the 3rd carbon of this parent chain. And so if we wanted to name this compound, let me just redraw it. So we have a 4-carbon compound. And let's just say that we have an iodine here. You know what? Let's just do 2 iodines. Let's go crazy. right? And so let's just say that we have two iodines on this carbon chain. Then the parent chain, or the name of the parent, is going to be 1, 2, 3, 4. So it's still butane. Erase the E because I have an amide. So this is butanamide. Now, since I have two iodines on carbon 1, 2, 3, and 4, so it looks like I have two iodines on carbon 3 and 4. This is going to be 3, 4 dash diiodo. And then since there's no other items for me to name, I'm going to merge that with a parent name. And the last thing I'm going to describe is the N-methyl. And so that goes in front of the substituent 3,4-diodo. So I have N-methyl. And then I'm going to put a dash between the L and the 3 because I'm going from a letter to a number. And so this would be the name of this specific organic compound. Okay. All right, so let's go ahead and take a look at another example. Here we have my carbonyl group. So any carbons that's attached to that carbonyl group, that's probably going to be my parent chain. And so this is going to be my N substituent. So this is going to be N-ethyl. Okay. And so if I have N-ethyl, let's see here. I need to describe my parent chain. So this is a 2-carbon compound. And so that's going to be ethane. Drop the E, add the amide, since I have a secondary amide. And so you don't put in like secondary amide in the name, you just say amide. You're just going to have to look at whether or not there's like an N substituent to determine if it's a secondary, tertiary, or primary amide. Since there's no other substituents on this parent chain, combine these two pieces. So I have N-ethyl, ethanamide. And I'm done. Okay. So let's go ahead and take a look at this last compound. You know what, instead of naming this, I'm going to redraw it to add some substituents to kind of give it more flavor. Instead of 4, let's do this. Let's make it more exciting. Okay. So we're not going to name this. If you guys want to name it, the answer is on the notes portion of my PowerPoint. But I want to do something a little bit more exciting. And so I want to do a double bond here. Let's go ahead and do this guy, and then let's go ahead and do okay. All right, so let's go ahead and name this specific skeletal structure, this organic compound. And so I recognize that I have an amide and that this is my carbonyl group. And so therefore, this is probably my parent chain. And so here I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 doesn't matter. So I'm just going to go straight across. And so since I have a 6-carbon parent chain, this is going to be hex. So I'm going to say hexane for now. Oh, but look, there's a double bond. And so it can't be hexane. It has to be hexene. And let me see here. Oh, look, there's an amide. And so it's not hexene. It's hexanamide. And so now that I've named this portion, I just have to indicate to the reader where that double bond is located. Where does it start in my carbon chain? And so if I number my carbons, I have 1, 2, 3, 4, 5, 6. So it looks like my double bond starts on carbon number 2. So that means I need to put a 2 in front of the hex. And that tells me that the En, which represents my double bond, is going to be on carbon number 2. So I have 2-hexenamide. That's cool. Let's go ahead and name our last two substituent. So we have a fluoro and we have an ethyl. And so they're both on carbon 4. And so since we have two different substituents, we just need to figure out which one we're going to name first. So here E comes before F, so you have to do it alphabetically. And so for the one that I'm going to name first is 4-ethyl. So I have 4-ethyl. And then now I can go ahead and put in the fluoro. So I need to kind of scoot this just a little bit, give some room. So dash 4-fluoro. And I'm going to go ahead and move this guy a little closer. And I'm going to put a dash between the O and the 2. So I have 4-ethyl, -4-fluoro, -2, -hexenamide. Okay. Now we're not done yet. The reason why is because we've only described everything to the left of this nitrogen. Now we need to describe this carbon chain that's on the nitrogen itself. And so this is a 1, 2, 3 carbon substituent that's bonded to this nitrogen. So this is going to be N-propyl. And all of this needs to be placed in the very front. And so I'm going to go ahead and move this name just a little bit further to the right. And I'm going to add N-propyl in front of everything. And that is going to be the name of this organic compound. Now, if I were to give you the name, and if I want you guys to draw the structure, you guys can go ahead and work backwards. First, identify the longest carbon chain, the parent chain. That's hex, that's 6 carbons. 1, 2, 3, 4, 5, 6. It looks like you have an amide. So on one of the ends, I'm going to put a nitrogen. So here's carbon 1, 2, 3, 4, 5, 6. It looks like I have a double bond on carbon number 2. So I'm going to put a double bond there. I have a fluorine on carbon 4. I have an ethyl on carbon 4. So that's 2 carbon chains. That's a 2 carbon chain. And then I have an N-propyl. So on my N, I have a propyl group, which is a 3 carbon compound. 1, 2, 3. And so this this nitrogen is bonded to 1, 2R groups. So this is a secondary amide. And that means that I need 1 hydrogen and a lone pair. Okay. And that's going to be the organic structure for this specific compound. Notice It should be very similar to the original. But hopefully you guys are picking up the pattern on how to convert the name to its structure. Okay. Let's see here. For this one, I'll go ahead and name this really quickly. So notice that I have my amide here. So this is carbon 1. Here I have an N-ethyl. Here I have 1, 2, 3, 4. So this is but. And then I have a double bond. So that's butene amide. Double bond here, amide. That double bond is on carbon number 2, so this is 2-butenamide. And I have no other substituent except for the N-ethyl. And so what I'm going to do is I'm going to put N-ethyl at the very front, and then put a dash. So the name of this organic compound is N-ethyl-2-butenamide, where the double bond is going to be on carbon number 2. Okay. So the last compound that we're going to learn how to name are tertiary amides, very similar to tertiary amines. So once again, find the longest carbon chain that has a carbonyl group. You're going to change the suffix to amide. It's not necessary to indicate the position of the amide since the carbonyl carbon is directly connected to the nitrogen. So you don't need to put the 1. You give the carbonyl carbon the lowest carbon number. Very similar to secondary amides, you're going to use the capital M to designate the alkyl groups that's attached to the nitrogen atom. And then you guys are going to arrange in alphabetical order the alkyl groups that's not part of the main chain. And these N alkyl groups will be described first before any substituents. So let's go ahead and take a look at our last 4 or 5 examples. So looking at this first organic compound, I see my amide. Notice that's 1, 2, 3 R groups. They're all carbon-based, so this is CH3, CH3, and then this is an acetyl group, okay, 2-carbon compound. And so since this is my carbonyl, this is my longest carbon chain, so that is going to be a 2-carbon compound, that is ethane. Drop the E, add in the amide, so this is ethanamide. No substituent on the parent chain, and so I'm going to describe my other 2 R groups. So for my other 2 R groups, I have 2 methyls, so that's going to be N, N dash dimethyl ethanamide, and that's the full name of this organic compound. So it's very similar to tertiary amines. So I apologize, my throat is dry. And so let's go ahead and look at the next organic compound. So here we have 1, 2, 3 different R groups. So this is a tertiary amide. And since this is my carbonyl group, everything that's connected to the carbonyl carbon, that's going to be my parent chain. And so on my parent chain, I have 1, 2, 3, 4. This is always carbon number 1. So I have butane, no double bonds. Erase the E, add the amide. No other substituent, so I'm good to go. So that this part is done. So look, looking at the bottom, I have an N-methyl. I have a N-ethyl. And so since E comes before M, the N-ethyl has to be written first. So this is N-ethyl dash N-methyl butanamide. So once again, we have to put the dash because this N is not really like a letter. It's more of, well, it is a letter, but it's representing the nitrogen. And so we're going to treat this as if it was like a number. Okay. And so the final answer is N-ethyl, N-ethyl-N-methyl butanamide. And so let's go ahead and spice this up. Let's just say that there's, I don't know, like a double bond, and here there's going to be, let's do a chlorine group, right? So how would you name this compound? Well, our N-ethyl and N-methyl is going to stay the same. We're not going to add substituents on these other carbons just because it makes naming this specific compound beyond our reach for this semester. That's for the full year of organic chemistry. So technically you can have, like, for example, a bromine here. But naming this, you would have to change the name of the N-ethyl, and that's going to be out of the scope for this class, so you don't have to worry about that. But you should be able to name the substituents and double bonds for parent chains. That's something that you guys are capable of naming at this point in time. And so since this is carbon 1, this is carbon 2, this is carbon 3, carbon 4. It looks like I have a 2-chloro. And I have on carbon 2 the beginning of a double bond. And so the name of the parent chain is going to be butane. Okay, so sorry, a butene, which I'm going to raise the E, so this is butane. And then since I have an amide, I'm going to go ahead and put in amide. And so I need to communicate to the reader where the double bond is, not so much where the amide is, because I always know that's carbon number 1. And so I'm going to put 2-butanamide to indicate to the reader that the double bond is on carbon number 2. And I already know that the carbonyl carbon of the amide is always carbon number 1, so that doesn't matter. In other words, you don't have to split this, amide and then put a 1 in the middle. So please don't do that, because your amides the carbonyl carbon on the amide is always carbon number 1. All right, so now that we have the parent chain, we're going to put all the pieces together for this modified organic compound that I just drew. The first thing that I want to write are my N groups, my N substituents. So once again, I have N-ethyl dash N-methyl. And then it looks like I have to put a 2-chloro first, because that's a substituent before the parent chain. So now that I have the chloro, I've described the chlorine group, that's a substituent on the parent chain. I'm going to go ahead and name this portion, or just copy that portion, which is the parent. So this is going to be -2-butanamide. So this is the name of my organic compound. And once again, just to demonstrate how to draw this structure from its name, I'm going to find the parent chain, which is 4. So this is 1, 2, 3, 4. and then my amide, meaning I have a carbonyl group and a nitrogen. So since I have a double bond, that's on the second carbon. This is carbon 1, this is carbon 2, so I have a double bond here. Looks like I have a chlorine on carbon 2, so I'm going to put a chlorine. And then notice I have an ethyl and methyl, so on the nitrogen, I have to have an ethyl and I have to have a methyl. After you guys have drawn this, then and only then can you determine if it's primary, secondary, tertiary. Well, technically speaking, you know if it's primary, secondary, tertiary based on the number of ends you have. Okay, so if you have 2 ends on an amide, then my screen froze. Jeez. So if you have 2 ends on my amide, then you know that this is tertiary amide. If you only have 1 N, like only an N-ethyl, no N-methyl, on an amide, you know that's a secondary amide. And if you don't have any N's, no N-ethyl, no N-methyl, no N whatever, and you only have, for example, 2-chloro-2-butenamide, if you only have this portion, then that's a primary amide. Okay. All right, so let's look at our last example here. I have 1, 2, 3 carbons bonded to the nitrogen, so that is a tertiary amide. So since I have 2 ethyl groups, this is going to be N, N diethyl. And so looking at the carbon parent chain, I have my carbonyl group. That's going to be carbon number 1. And so that means that I have 1, 2, 3, 4. So I have a 4 carbon chain, 2, 3, 4, in which I have a methyl on the 3rd carbon. So since I have a methyl on the 3rd carbon, I need to add this after the NN diethyl because this is a substituent. And so my screen froze again. And so I'm going to go ahead and write N, N dash diethyl dash 3 dash methyl. Okay, and so this part completes naming this and this. So that checks off. This part finishes naming this portion of the organic molecule, leaving me with just this part to name. And so since it's a 4 carbon compound with no double bonds, this is going to be 3-methyl butane, right? It's a 4 carbon compound. Now I'm going to erase the E, put an amide, and I'm done. And my screen froze again. All right, so the name of this last compound is going to be N, N dash diethyl dash 3 dash methyl butanamide. And so there are these benzene rings. You guys can go ahead and look at the answers on the PowerPoint. So please open the PowerPoint version, not the PDF. Scroll to slide 131. And then at the very bottom, there's a notes section. And the notes section will already give you guys the name for these compounds. And so just to verbally say it, so this first one is going to be N, N. So N, N dimethyl. And then this is going to be benzanamide. I'm sorry, not benzanamide, benzamide. Benzamide. And then so for this one over here, the second one, the answer is going to be N, N, dimethyl. So that will, stating this will finish this and this. And so here I have two substituents on the benzene ring. So this is carbon 1, 2, 3, 4, 5. So it looks like I have a 3-methyl and a 5-methyl. So then I have to put dash 3, 5 dash dimethyl. And so what I'm going to say afterwards is benzamide. Okay. All right. And so this is carbon 1, 2, 3, 4, 5, 6. So remember, benzene rings can be represented with a hexagon and a circle inside. Okay. So the last one is going to be N, N dash, oops, not N, N. This is methyl ethyl. So N dash ethyl, E comes before M, dash N dash methyl. And so this portion right here is just benzamide. Okay. All right, so that pretty much finishes naming amides. And that's it for this lecture video. All right, guys. See you later. Bye.